Hello, dear students. This is Dr. Emmanuel here again with the weekly summary for week 3 for CV013. In this video summary, we will move from general design principles to the actual behavior and design of reinforced concrete beams in bending. So the focus is on how reinforced concrete beams resist bending, the assumptions we make in design, how a beam behaves as load increases, and how we analyze singly reinforced. Good. So we will now look at the general principles of reinforced concrete beam behavior. So as we already know, concrete is strong in compression, but concrete is weak in tension. On the other hand, steel is strong and ductile in tension. So in a bending beam, concrete resists compression and steel resists tension. This is why reinforcement is placed near the tension zone of the beam. So let's take this diagram for example. We have a concrete beam that is simply supported. If we apply an action on this beam, say a uniformly distributed load, what will happen to this beam is that the beam will deflect. So the beam deflects downwards. So the new shape of the beam becomes something like this. In this form, the beam is in compression at the top, while the bottom fiber of the beam is in tension. Because concrete is good in compression, but poor in tension, and on the other hand, steel is good in tension, we place the steel at the bottom edge of the beam. By so doing, the top of the beam resists compression where there is concrete, and the bottom of the beam, because of the presence of the steel bar, resists the tension. So this is the concept behind reinforced concrete design. Steel is placed in the areas of the concrete where there are tensile stresses. Alright, now let's look at the key assumptions of the Eurocode 2 design philosophy. To make design manageable, first of all, we assume that plane sections remain plane after bending. 2. We assume that perfect bond exists between concrete and steel. 3. We assume that tensile strength of concrete is ignored at ultimate limit state. And 4. Stress-strain relationships are idealized. These assumptions allow us to convert a real beam into a calculable model. Next, we shall look at the stress-strain behavior of concrete and steel. Concrete has a nonlinear stress-strain curve. So if we take concrete to the lab and we test concrete in compression, we're going to have a behavior of concrete that is first elastic and then it reaches a maximum and fails, fractures suddenly. On the other hand, if we test steel in the lab in tension, it first acts as a linear elastic material and then behaves as if it wants to fail, and then there is a strain hardening in the steel, and then it becomes plastic for a while before it fails finally. So the failure is ductile failure. So the maximum strength of the concrete is called the characteristic strength, FCK. And the point at which the steel becomes nonlinear, from linearity to nonlinearity, which is that point, is called the yield stress or the characteristic yield stress. Also, please note for steel, we have two types of strength. We have the maximum strength, which happens to be the most maximum strength that the steel achieves, which is FYU, is a maximum strength of the steel. But in design, we make use of only the characteristic yield strength. So what then happens is that we use the design strength for both materials. So for concrete, we reduce the material strength by a partial safety factor for concrete. And for steel, we do the same thing. We reduce the material strength by a partial safety factor for steel. Due to the long-term effects in concrete behavior, the characteristic strength is usually taken as 85% of the actual characteristic strength, and the partial safety factor for concrete is 1.5. Therefore, the design strength for concrete is 85% of the characteristic strength divided by 1.5, and that will give us 0.567 FCK. We do something similar for steel. The partial safety factor for steel is 1.15. So the design strength for steel is the characteristic strength of steel divided by the partial safety factor. And that gives us 0.87 FYK. And these are the values that we use in design. Now we must also understand that the ductility of steel is what is responsible for a warning before failure in reinforced concrete design. And this is a good property because we don't want sudden failure in our materials. Good. Next, we shall now look at the behavior of a beam under bending. So when we load a beam, as the bending moment increases, the beam goes through 3 stages. The 3 stages are the uncracked stage, the cracked stage, post-yield stage. In the uncracked stage, the concrete resists both compression and tension, so there is no visible cracks and the behavior of the beam is linear and elastic. In the cracked stage, the concrete cracks in tension, and in the post-yield stage, the steel yields. Concrete compression zone governs, and the beam approaches its ultimate capacity. So these are the 3 stages that govern the behavior of a reinforced concrete beam as the load increases. It also causes the bending moment to increase. Next, we are going to look at the notation and geometry for a singly reinforced beam.